In this third and final video of section 10.1, we're going to talk about curves and convex sets and eventually get into different two-dimensional figures like polygons. And so if you just grab your pen or your pencil and you start writing and drawing and moving your pen around and looping it this way and that, there are three different things that could happen. One, you could get something that looks like this. Two, you could get something that looks like this. And three, you could get something that looks like this. So take a moment and see if you can notice the difference between the three drawings, the clear difference between the three drawings that I just did. In the first one, I just started drawing a line. It started here and it ended here. In the second one, I started drawing a line here, and then I ended in that same spot. In the third drawing, I started here and ended in the same spot, but these two figures were still different. In this one, I never overlapped myself, but in this one, I did. So those three different situations all have names. And here is what those are. And you'll need to be able to identify those. So the first one is called a simple curve. So in the examples you see down here, curve A is a simple curve. What's the unique information about it? It stops and starts without intersecting itself. Okay, so it starts and then it stops, but it never actually it comes back to the end. Okay. Now B is called a simple closed curve. It's also a simple curve, but it does start and stop at the same point. Now curve C is a closed curve, but it did intersect itself. And so it's not a simple closed curve. Okay. So C is a closed curve, but it's not simple because, again, it didn't intersect itself. And actually, going back to my drawings, there was a fourth one that I probably should have drawn. One that just starts here and goes like this, right? So this is actually different from the first one that I did. It started and stopped, but it never crossed over itself. So this was simple. This was simple closed. This one was closed. And what was this very first one that I did? It was actually none of them. It doesn't fall into any of those classifications. Okay. So simple means it doesn't cross itself. Simple closed means it doesn't cross itself and it ends it where it started. Closed means just it ends where it started, but it crossed itself. And if it crosses itself but does not end where it started, then it's none of those three. So here, go ahead and try to classify these four as the one of those three that I just mentioned. So number one is a closed curve. It starts and ends, but it crosses itself. Number two is simple. It never crossed itself, but it started and ended at different spots. 3 and 4, those are both simple closed because they never cross themselves, but they also start and end at the exact same spot. Now, we know what a plane is, right? A plane is a flat surface that sort of goes on forever. But a lot of times we are looking at just a section of a plane, and that's called a plane region. Now, here is the sort of, I don't know, a bit wordy mathematical definition. It's the union of a simple closed curve and its interior. What's a simple closed curve? Well, something that looks like this, we just learned, and its interior. So all the space on the inside of it, all right? This is all the interior. That whole, all of that section, right? The curve itself and its inside is called a plane region. Now, a plane region can be classified two different ways. It can be concave or it can be convex. So, what did those terms mean? Do you already know? So, again, if we want to be really mathematically precise, we can do that. But I always just like to think of something that's concave as something that's caved in. So I might look at, say, this picture right here, and I note that it has a section that goes in. A way we can test to see if something is concave is what you see here with this line segment, X to Y. If you can pick 2 points inside your figure, connect them with a line. If that line exits the figure, then it's going to be concave. If it's not concave, then it is convex. Convex never comes in on itself. You can pick 2 points anywhere in this figure, connect them with a line, and it'll never exit the figure. If you connect 2 points within the line, it'll never exit the figure. So those are convex figures. So here again is another check for you. Those 3 figures, label them as concave or convex. Figure 1, a circle. This is convex. It never comes in on itself. 2 is concave. It comes in on itself right there. We could connect these 2 points here, and it exits the figure. A triangle is convex. It never caves in on itself. So let's examine a really special type of figure. It's a special type of a simple closed curve, and it is the circle. Now, circles have lots of terminology that go along with them. Here are 4 of those terms. So the red line on the outside is the circle. Let's start with the diameter. If you, first of all, find the center of your circle, that's the center, and you draw a line from one side of your circle to the other side, going directly through the center, that is called the diameter. It's the distance from one side of the circle to the other. If you want to calculate half of that distance, or from the center just out to the edge, that is called the radius of the circle. The radius is always half as long as the diameter. If you pick some random point on the circle and go to some other random point on the circle, not across the middle, that's called a chord. So again, a line segment whose endpoints are both on the circle is called a chord. And a tangent, the tangent is a line that only touches the circle at one point. So a tangent is like imagining a picture of a bowling ball sitting on a desk, and then you put a board on top of it, right? That bowling ball and that board are only going to touch at one very specific point, okay? And that is called the tangent line. And then finally, it's not shown on this picture, but the distance around the circle. So if you could lay this circle flat on the ground, open it up and lay it flat, or measure it from that point all the way around back up to itself, that is called the circumference. Circumference is the distance around the circle. So a circle, again, is this perfect little mathematical geometric figure where every point on the circle is the same distance from its center. But there are many other different types of simple closed curves, and we call them polygons. So let's take a moment to investigate different types of polygons. So again, polygon is if we want to look at the very official definition, it's a simple closed curve that's the union of line segments. And the union of a polygon and its interior is called the polygonal region. I know that's a mouthful. But really, we classify polygons and we can think about them as just two-dimensional figures that have straight sides. That's another way to think about a polygon. They have straight sides and they come together at a specific point or the same point. So we classify polygons based on the number of sides that they have. And so here are some of them, not all of them, but we are familiar with a three-sided polygon. Notice how it has three straight sides. It can look a lot of different ways. As long as it has three sides, it's a triangle. If it has four sides that are all straight, we call it a quadrilateral. If it has five sides, it's a pentagon. Notice these prefixes all refer to the number of sides. Six sides is a hexagon. Seven sides is a heptagon. 8 is an octagon. 9 is a nonagon. 10 is a decagon. And 12 is a dodecagon. And so those are some common polygons. Poly means many or any number of, and these are very specific types of polygons. You want to be familiar with those. The line segments are their sides, right? So polygons have sides, those line segments that come together. The endpoints of any polygon, where those sides intersect, those are called the vertices. That's plural of vertex. Again, two sides of a polygon are called adjacent if they share a common vertex, like this side and this side are considered adjacent sides. Again, because they share a common vertex right there. And two vertices are considered adjacent if they share a common side. So these are called adjacent vertices. Vertices. Because they both share that side. For an example of what would not be adjacent, so this vertex and that vertex are not adjacent. Because they don't share a side. This side and this side are not adjacent because they don't share a common vertex. So, based on what we've learned about polygons, here are some pictures. And your question is, which of those are polygons? Based on what we know. If you'd like to see the definition again, it's a little complex, but that's the official definition. So this might have been a little bit of a struggle for you. Maybe you were wondering. So I'm going to take a moment to get there. So they have to be a simple closed curve. Polygon has to be a simple closed curve. Well, that means it can't have any intersecting lines in it, and it has to start and end at the same place. Well, that rules out this one because it's got this little extra line over there, so it intersects itself. Same thing with that one. This third one, or this fourth one, is not a simple closed curve. Okay. Because it's got, again, a curve and then another curve on the inside of it, right? These don't have line segments. They're not straight lines. Only number 2 is a polygon. They have to have straight sides, straight line segments. So any polygon, other than a triangle, has what we call diagonals. And what is a diagonal? You can see diagonals of this pentagon here. Diagonals are, I'm going to copy the official definition for you. Any line segment connecting one vertex of a polygon to a non-adjacent vertex. And so all of these lines, dotted lines that you see here, are connecting one vertex to another vertex, this vertex to that vertex, and so on and so on. And those are called diagonals, diagonals. This pentagon, as you can see, has 5 diagonals. 1, 2, 3, 4, and 5. And there are interesting mathematical properties and numerical properties about how many diagonals certain figures has. So let's move on to triangles, because we have several different types of triangles. Triangles we know have 3 sides, and we can classify them in a number of different ways. So just like we had angles that were acute, we can also have an acute triangle. An acute triangle means that all 3 of its angles are acute. And acute means they are less than 90 degrees. So that's an acute triangle. We also had right angles. We can have a right triangle. So a right triangle is 90 degrees in one of its angles. So as long as it has one right angle, and it can only have one right angle, then it is called a right triangle. I'm going to jump down here. When we were learning about angles, if an angle was more than 90 degrees, then it was called obtuse. And you can see this triangle has one angle that's obtuse. So if that's the case in a triangle, then the triangle is called an obtuse triangle. Let's go back up here. If all 3 sides of a triangle are equal in length, then it is called equilateral triangle. Completely opposite of that, if all 3 sides are different lengths, all 3 of them are different, it's called scalene. And if at least 2 sides are of equal length, those 2 are equal, so at least 2 sides are equal length, it's called isosceles. So again, these are terms that you will want to be familiar with. So again, 6 different ways we can classify our triangles. So let's jump to quadrilaterals. Quadrilaterals have how many sides? 4. So let's look at some different 4-sided figures. So one of our 4-sided figures is called a trapezoid. And a trapezoid has exactly one pair of opposite sides that are parallel. So this side right here and this side right there are parallel, but these other sides are not. Another way to envision a triangle or a trapezoid is a triangle that had its top cut off. So if you cut off the top of a triangle, you'll be left with a trapezoid. An isosceles trapezoid, just like an isosceles triangle, has equal length sides. The non-parallel sides have equal length. I'm actually going to jump down here. A square. We're familiar with a square, maybe one of the first shapes that we learned. All sides are equal length and they're all right angles. So we have 90 degrees, 90-degree angles. That's called a square. Right above it, we have a rhombus. Well, just like a square that has all sides of the same length, a rhombus has all sides that are the same length, but the angles are not. The opposite angles are the same, but this angle and this angle, not equal to each other. Just all we can say about a rhombus is that the sides are equal. A parallelogram means that pairs of opposite sides are parallel and they're also of equal length. So this side and this side are parallel. They're also of equal length. This side and this side are also parallel. They're of equal length as well. And then a rectangle is really a parallelogram that has 90-degree angles. Pairs of opposite sides are parallel and equal length, and it has all right angles. So to kind of put a bow on this, we're going to do some true and false questions. I have 10 of them for you. And it's going to be asking questions about all of these different types of figures that we just discussed. And I'm going to put them all up here at once. Right next to each other. And what I recommend you do is pause this video, sketch some figures as it says. And what you're going to try to determine is whether each of these statements below is true or false based on those exact definitions for those figures. I'll do the first one with you so you can kind of see through the reasoning. It says every square is a rectangle. So is that true or is that false? Well, you've got to go back to the definition. A square just says all sides are of equal length and it has all right angles. Well, what's the definition of a rectangle? It's that pairs of opposite sides are parallel and of equal length, and it has all right angles. So does every square fit the definition of a rectangle as well? It does. A square is just a more restrictive rectangle. A square is a rectangle that all the sides also have to be equal. So every single square is also a rectangle. Take a few moments, pause this, and see if you can go through and answer true or false to every single one of those statements. Okay, so let's see how you did. Number 2 says every equilateral triangle is an isosceles triangle. Well, an equilateral triangle, all sides are the same. In an isosceles, it says at least 2 sides are the same. So yes, every equilateral triangle is an isosceles triangle. Number 3, some right triangles are isosceles triangles. Right triangle has to have a 90-degree angle. An isosceles triangle has to have 2 sides that are the same. You could have 2 sides that are the same and it be a right triangle, which means yes, some right triangles are isosceles, but not all of them are. Number 4, some trapezoids are parallelograms. Trapezoids have to have exactly one pair of parallel sides. So these sides are parallel, but it said it could only have one pair. It had exactly. Parallelograms have 2 sets of parallel sides. A trapezoid only has 1. So that is a false statement. Number 5, some isosceles triangles are scalene triangles. By definition, isosceles triangles have 2 sides that are exactly the same. By definition, a scalene triangle has no sides that are the same. So that is a false statement. Number 6, some isosceles triangles are obtuse triangles. Well, to be isosceles, it has to have 2 sides that are the same. But it could be an obtuse triangle if it has that one really big angle that's greater than 90 degrees. You can still have 2 sides that are equal. So that is true. Number 7, a rectangle is a parallelogram. A rectangle looks like this. All opposite sides are parallel. That's the definition of a parallelogram. Opposite sides are parallel. So that is true. Every rectangle is also a parallelogram. Number 3, some rectangles are isosceles trapezoids. Well, to be a rectangle, it has to look like this. To be a trapezoid, it can only have one side of, or one set of parallel sides, even if it's isosceles. And so a rectangle is not an isosceles trapezoid, and it can't be. because an isosceles trapezoid has to have one set of non-parallel sides. Hold on. Number 4, some right triangles are scalene triangles. Yep. So right triangles, again, all they have to have is a 90-degree angle. To be scalene, all the sides have to be different side lengths. So you can have a right triangle with 3 different side lengths. So that is true. Just some of them. Doesn't mean all of them, but some of them can. And finally, some scalene triangles are acute triangles. So to be scalene, all the side lengths are different. To be acute, they all have to be under 9, all the angles have to be under 90 degrees. So you could have a triangle where all the angles are less than 90 and all the side lengths are different lengths. So that is a true statement. This exercise was actually very similar to what we worked on in the previous chapter when we learned about all of the different types of numbers, irrational numbers, rational numbers, whole numbers, integers, and we worked on classifying those numbers. A number can be an integer, but it can also be a rational number. But you can have a rational number that's not an integer. And so students, young students, can develop that conceptualization of classifying things with figures, shapes that they can touch with their hands, as long as they can learn those definitions, and develop that skill before they go on to work on classifying the number systems like we learned last time. Now, if you're following along with the slides, I'm going to put one final slide up, though I'm not going to get into it. It's just more of an activity that I would think is valuable for you to do. The slides have a little more discussion, but it's just sort of a challenge question based on some of the information we talked about. We talked about diagonals and polygons, and so a 12-sided polygon, I left with the question of how many diagonals it has. And if you can just try this. Again, work through some of the information that's on those slides. I think it's a good exercise for you to explore and look for, again, patterns that start to occur in these polygons and their diagonals.